Now we want to see how we can design a slab and concrete walls. So I back to undeformed shape, show all, and I move on to reach to one of the walls, and I need to come here, put this one in view. Now I can see the walls. So this is one of the retaining walls we have. Now see how we can design this retaining wall. I can come here into shell options, and here I have concrete design. When I click on concrete design, it gives me these options. What I have here is some of them are similar as what we had before. So visible face, top face, and bottom face. That means you can see them here, or maximum or minimum or absolute maximum. Here are the components that you can check. N11, N22, N12, Nmax and min, Ndesign1, Ndesign2, and AST1, AST2, and also FC and SC. So what is N, and what's the difference between N and F that we had before, F11, F22? So if I come here in resultant force, I have F, but in concrete design I have N. So there is a document for shell design that I share with you guys that you need to study, and here is explained that a part of area of concrete equal to twice of the concrete cover, or some other criteria that mentioned here, that the distance from the center of the slab to the center of the outer reinforcement, that will be continued as the area that SAP will check all the stresses and check what is the tensile load here, and then based on the calculation transfer this tensile load to reinforcement and calculate the reinforcement area. And the same for the bottom part. This specific area is calculated just for the tensile for the reinforcement, and also the same for the compressive stress, and here is the core. So the formulas are here, but after calculating all axial forces and stresses due to moment or due to in-plane axial loads you have. This is generally not what we do when we design a slab or wall. We either consider axial load due to in-plane moment or out-of-plane moment, but SAP add them up together. So somehow the result of this axial loads for design of reinforcement is more accurate when it is done by SAP. And it shows you that this N coming from both moment and axial load together, and when you get this one, then it will be add up to the absolute value of F12 as well. So F11 plus F12, also F22 plus F12. So this is the summation of all loads and axial loads that cause tension in that layer of concrete. And then simply coming here and mention that reinforcement shall be designed based on this formula. Ndesign1 top divided by 0.9 Fy. So this is the tensile capacity of the reinforcement, and based on that the area of the reinforcement will be calculated. So AST1 is along axis 1 and AST2 is along axis 2. So you have top and bottom reinforcement separately. Also you can calculate the axial compression, which is coming for CT1 and CT2. If you back to top here, you see CT1 and CT2. So this area you can see the maximum compressive stress or maximum tensile stress. Compressive stress will be taken by concrete, and tensile stress will be taken by reinforcement. So let's see what we have here. So if I come here and say, for example, come UG2, and I want to see N22, which is in this direction, because one is axis 1 is horizontal, axis 2 is vertical. You see the numbers here. So it's coming about 135 Newton per millimeter. So if I change this one to kilonewton per meter, number would be similar based on transferring the load. So you will have the same numbers and 135 here. So this is axial load you have in this wall. So this is for bottom face, if you go to top face, you need to check again top and bottom, based on the axis tree. So if, for example, axis tree here is out of plane towards you from the monitor, so bottom would be the back of the wall, top would be the visible face of the wall that you can see now. And this is N11, N22. Then when you come to AS, change it to Newton and millimeter, and the ratio you see here, this is a square millimeter per millimeter reinforcement intensity ratio. If you want to see how much reinforcement you need for AST1, which is horizontal reinforcement, for example, here is 158 multiplied by 1000, it gives you 158 square millimeter per millimeter for the top face horizontal reinforcement. The same for AST2, if you apply, it gives you the vertical reinforcement. So you see, vertical reinforcement is different because some areas you have pile and transferring load to the piles, causing this because you have a kind of a span here, and this beam wall is spanning between piles and transferring load from columns to the piles. So this number here are more than here. You see the ratio change. So you need to see what's the ratio you have in each range. You may go for the maximum one, but you can't average here and here together because definitely you need more reinforcement here. So you need to see if the ratio is reasonable and you can accept it, then you can use it for all along the wall. Let's go to one of our core walls. Okay, so here is our core wall, and I want to check what reinforcement ratio I need here. So this is for comb UG2. If I want to check the reinforcement ratio, I need to come to envelope U. That gives me the maximum reinforcement at each area, and that is what I need. So if I apply, so you see the ratio here is 4.9 up to 1 even at the corners. So how I can use this one? I want to, for example, have a reasonable reinforcement arrangement here. I want to go for, say, for example, N12 at 200 millimeter. So N12 at 200 millimeter would be 565 square millimeter per meter. So if I come here and use the define contour and put here 565.565 and here, so this is a minimum, I can keep it the same, 0.565, and press apply. So you see the whole areas are more than 0.565 is showing here. So the areas are less, they are one color, the areas are more, they are one color, because I just use one ratio here. And you see that the areas are overstressed, so probably this is not the right reinforcement ratio for you. If I go for N16 200, so the ratio would be 1, which is 1000 millimeter per meter. So if I press apply, it shows me less area that I need more reinforcement. I may add some extra bars here and strengthen the corners, and then N16 200 probably would be acceptable. The same for AST1 for top face and bottom face. That's how you can figure out what's the number. The range here would be the same because you have just one ratio of reinforcement in your design. There is another way that you can use, I will show it in the slabs, that how you can utilize the capacity and see what needs to be defined as reinforcement. So this is basically the concrete design. If you look at the document, you see this is based on Eurocode. This is the Eurocode that we're using, is 1992, but that's the only option available for this design. So it's a good cross check for you guys. You can design it manually based on your own method, and that's a good indication to see if there is anything missed, where you need any extra bars, and just for your double check, that would be a perfect method. The other thing I would like to share with you before move on is FC and SC. FC is the force based on kilonewton per meter or any unit you use here for that specific thickness of the element that I mentioned here. So roughly twice of the cover of the reinforcement. So what is the force here is axial force, and divided by this thickness gives you the stress. So the formula are mentioned here, so you can come down and have a look at this. So the FC divided by 2 times of minimum CT1 CT2 is the compressive stress. So if I come here, I want to check compressive stress. Sometimes we are after the average compressive stress in the wall to see if there is any boundary element here, if the stress exceeded of some certain amount, for example 15% or 20% of the concrete strengths. But this doesn't give you that indication. This SC, if I put -8 here, for example 20% of 40 MPa, this is axial stress I am after, but I need it for the whole thickness of the wall. What it gives me is just for that specific area around the reinforcement, not for the whole core wall thickness. So you see the numbers will be excessive here. So here is a less than 8, but here coming to 15, 17, 25, which is not very normal for the whole thickness of wall for such a small building. Even for 12, 15 story building, you wouldn't have such a big stress at this level. Depends on, of course, the arrangement, but that's not very normal. So this is for stress. Now let's move on and let me show you one slab, and then we can finish this video. So this is a slab as Z 8 meters. So if I come here and choose shell concrete design, and for example here I want to see if I need any reinforcement ratio more than my preliminary proposed reinforcement ratio, which is, for example, N12 at 200 gives me 0.57 square millimeter per millimeter. If I apply, I can see which areas I need more reinforcement. So in these two areas I need more reinforcement. For one direction, for AST2, I have just these two areas that I need more reinforcement. So the rest of areas are fine for N12 at 200. The other way we have is using the moment capacity. So I'm just putting in a deform shape first and change this unit to kilonewton a meter. So if I get back to the same menu, but this time I choose resultant forces and say, okay, for example, the capacity I have for this slab based on the reinforcement I chose is 20 kilonewton per meter. How can I figure out if I have areas over stress and I need more reinforcement? So the easiest way is check bottom and top reinforcement separately. For example, here the range is good for bottom reinforcement because the numbers are positive. So I said, okay, 20 is my capacity. So whatever is less than 20, I don't want to see that. Whatever is more than 20, I'm interested to know where they are. So if I press this, I can see just this small area is more than 20 kilonewton meter per meter, and the rest of areas are fine. So I don't need any extra reinforcement. Somehow it's consistent with what you saw in the reinforcement intensity ratio contour. But if I want to check top reinforcement, I need to put, for example, here from -20 to -50. Yep. So -20 is the capacity. I want to see what is less. So this is minimum and this is maximum. So maximum for me is here. For top reinforcement, you need to lock the maximum and give a smaller value for the rest of overstress area. When you're checking bottom reinforcement, you need to lock the minimum value to your capacity and give a larger number here and see what is coming up. So you see that just these 4 small areas, I need reinforcement more than proposed reinforcement arrangement I have, and the capacity requirement is more than 20 kilonewton meter per meter. And you can do the same for shear capacity and check it again, negative and positive for shear, because generally both sides of the columns you have two different values. So if I choose this one for V23 and just put here say minus so this is a minimum value minus 10, you see these numbers coming here, and this, you need to do the same for positive. So if I put here 0 and 0 for shear, you see these numbers are negative, this side is positive. So absolute value is important for you. It's not like moment for shear, because shear is changing from column. When you reach to the column, suddenly the sign of the shear will change, and from positive to negative. So just be sure that you choosing the right numbers, otherwise you may miss a part of the capacity. So absolute value in shear is important, but in moment, based on top or bottom, you need to go for negative or positive. Okay, so this is for reinforcement check of the slab, but the other option you need to check for a slab is deflection of the slab, and sometimes that deflection determines the thickness of the slab or concrete strength to increase the stiffness of the slab. So I'm coming here, put it on deform shape, and then come here to Newton millimeter, and if I want to check the displacement of the slab, I can come, for example, to comp SG2, which is for the gravity load for serviceability limited states, and then here I need to use a contour to show the color. Otherwise, we are simply just if I untick this one and press apply now, so you see if you move here you may see the numbers. So U3 is minus 54 millimeter here on the columns, but you don't see any color here, and because you don't have this joint here, so sometimes it's going to be picked up. So 61 millimeter. What is important to check the slab is you need to check the slab deflection based on local displacement, considering the supports are fixed, and you should ignore the displacement of the support. So 51 millimeter is already the displacement of the column here. So that shouldn't be taken into account to calculate the displacement or deflection of the slab. So deflection of the slab here is relative to the supports. If I come here and use the contour and go to UZ and press apply, you see the numbers are here are very excessive. So what options you have to see the accurate number? Personally, what I do, I remove all levels below and I just keep this level and levels above plus the columns below this level of a slab, and then put rigid support at that column level and then run the model again, and that's the good indication for me to eliminate all displacement due to other interactions for lower levels, and then I can see the displacement for this level of a slab and justify if it's okay or not. Roughly in concrete, the short-term deformation you see here times 3 would be your long-term deformation. I will keep the crack section here 0.35 and check my short-term deflection based on that. This is conservative. If you have any sophisticated software that can check all those deflections, that's perfectly fine. But if you don't have, be a little bit conservative in deflection and ensure that the serviceability requirements can be met. So this is what I do, and if I have any transfer slab and I want to get the transfer loads, I need to increase the stiffness sometimes locally to ensure that the deflections are matched with the type of a slab I have. For example, if the slab is post tension, I need to have a reasonable stiffness here, then I can get the transfer loads on this slab properly. I will discuss about this in advanced course in more detail. So we finished what I wanted to share about design of concrete elements, columns and beams for frame elements, and walls and slabs for shell elements. And our next video will be about design of steel elements, columns and beams and braces.